All right, guys, this is section 6.4. There we go. You should be able to see the 6.4 notes on your screen right now. It's over comparing linear and nonlinear functions. The completed notes to this are actually posted with this video for you to download to Notability and save. And so just make sure you watch the video. It's going to pause at some random spots and ask you a question about something you just saw in the video. So you're going to get points for watching the video, and then obviously points for doing the homework and turning in your work paper. So let's get started. It says, complete each table for the sequence of similar rectangles. Graph the data in each table and decide whether each pattern is linear or nonlinear. So here are a series of similar rectangles. Now, to be similar, we haven't really talked about this much yet, but to be a similar shape has to be the same shape but a different size. That's what similar means, the mathematical term for similar. You might think similar just means it looks kind of like it. Similar means same shape, different size when you're talking about it in math or geometry. And so they want you to look at what the perimeters of these rectangles would be if I plug in these values for x. So if I plug in 1 for x, the perimeter of this green rectangle would be 1 plus 2 plus 1 plus 2. That's a perimeter of 6. If I plug in 2 for x, okay, then that means it would be 2 plus 4 plus 2 plus 4. And that's referring to this orange rectangle right here that's obviously a little bit bigger. So that would have a perimeter of 4 plus 4, which is 8, plus 2 plus 2 is 4. So that would be 12. Okay. When I plug in the x for 3 for x, and I see this red rectangle, that's going to give me a perimeter of, let me just write it up here, 3 plus 6 plus 3 plus 6. I'm just plugging in, obviously 2x would be 6 in this case, and x is 3. So 6 and 6 makes 12, 3 and 3 makes 6. Now we're looking at 18, and you can kind of see the pattern here. When I plug in 4, it just keeps increasing by 6 each time. The perimeter is going to be 24. When I plug in 5, the perimeter is going to be 30. So let's go ahead and plot these points. 1, 6 would be somewhere in this area. Since it's counting by 5s, I'm going to go ahead and say that's 6 right there. 2, 12. 12 would be about right there, I suppose, just estimating. 3, 18. 3, 18 would be right in this area. 4, 24 is going to be right in this area. And then 5, 30 is going to be the nicest one I have here to plot, which is going to be right there. So when I graph this, that you can see the points do line up. So when it asks you if it was linear or not, we know that it is. And obviously it would go through the origin as well. So if I were to write an equation for this, it would be y equals 6x plus 0, or just y equals 6x. I know it goes to the origin because if I plug in 0 for x, then I don't have a shape anymore because it doesn't have a length or a width. And so it's going to have an area of 0. Okay. So now they want me to do the same thing, except now calculate the area, which actually will be a little bit easier to do. So when I plug in 1 for x, so make sure I answer, complete the table, graph the data, decide whether it's linear or nonlinear. So I'm going to, I didn't write it, but we'll just say, obviously, this is linear. For the next one, when I plug in 1 for x, this is going to be 1 times 2, which is 2 for the area, length times width for a rectangle. When I plug in 2 for x, this is going to be 2 times 4, which is 8. So it's still increasing by 6. You might notice that. Okay. When I plug in 3 times 6 is 18. Okay, so it's not increasing by 6 again. That's a different rate of change. So I'm already thinking this is nonlinear. When I plug in 4 times 8 is 32. And when I plug in 5 for x, the area would be 5 times 10, which is 50. So let's see what this looks like when I plot these points. 1, 2 would be right there, maybe a little bit higher up, I guess, maybe right there. Then the next one was 2, 8. Maybe a little bit lower, right there. Okay. Why does that keep moving? Geesh. Okay, leave it alone. Then we've got 3, 18. 318 is going to be right in this area. Then we've got 4, 32, which would be in this area up here. And then we've got 550, which is going to be right up at the very top of my graph. And so if I were to graph this, now I also know this one goes to the origin, because as we talked about, when you plug in 0, it's going to have an area of 0. Actually, I think I said area for the last one. If I plug in 0 for x, it's going to have a perimeter of 0 as well. I think I said area. I think I misspoke. But anyways, if I plug in 0, it has an area of 0. So I also know it goes to the origin, and it's going to look like this. And so it's going to look like half of a parabola. And so it's obviously going to be nonlinear. Okay, it's going to be nonlinear. Now I want you to notice something here. I told you that the rate of change was changing here. It increased by 6, then it increased by 10, then it increased by, what is that, 14, then it increased by 18. The rate of change is changing, but look, this is interesting. The amount that it's changing by is going up by the same amount. So it's increasing by 6, and then it's increasing 4 more, and then it's increasing by, no, I shouldn't say increasing by 4 more. The rate of increase is increasing by 4 more, and then the rate of increase is increasing by 4 more, and then 4 more. And so that's what makes this nonlinear. It's increasing at different rates, but the rate that it's changing by is always changing by 4. Okay, so it's definitely nonlinear for that one. Now, here are some definitions for us. It says the graph of a linear function shows a constant rate of change, which rate of change is another way of saying the slope. We know that. We know that lines have a constant rate of change. That's why they're straight and they don't curve. Okay? But a nonlinear function has a variable rate of change. The word variable means changing. That's why when you have a variable, like you plug in 1 for x and 2 for x and 3 for x, they call it a variable because it can change. So a non-function has a variable or changing rate of change, like we talked about. So its graph is not a line. That's what nonlinear means. Could mean that it curves, could mean that it's separate lines, could be a bunch of different things. Each table shows the height h in feet of a falling object after t seconds, at t seconds. Graph the data in each table and compare the 2 graphs. Okay, so let's look at the first one. They want us to graph when t is 0, h is 300. This is counting by 30s. So 300 would be right up there at the top when t is 0. Okay, it's a parachute jumper. So think about what kind of slope you think this is going to have, right? It's decreasing. Their altitude's decreasing as time increases. So we're looking at a negative slope here. 1 second later, his altitude is 285 feet. Okay, so if this is 270 and this is 300, 285 would be right between those numbers. Okay, be 15 lower. And then at 2 seconds, it's at 270. It's kind of looking linear right now. Let's see if that pattern continues. At 3 seconds, it's at 255. At 4 seconds, it's at 240. Yeah, that makes sense. I guess I should probably lower my font size if I'm going to write this. 300 would be right there. Okay, so this is linear. And if I draw the line out, it's going to look like this. And so if I were to extend the line, I could actually find out where it's going to cross the x-axis. Because it is linear, I can actually write an equation for it. It has a negative slope. Each second, it was decreasing by 15 feet. So negative 15x means that's decreasing by 15 feet a second, and it started at 300. Okay, so that would be the equation for it, and it is definitely linear, or else I wouldn't be able to write it in slope-intercept form. Okay, so each table shows graph the data and compare the two graphs. Okay, so I know that one's linear. I'm guessing this other one's not going to be linear. You're dropping a bowling ball. I want you to think about that. If I hold a bowling ball over your head, 1 inch above your head, and I drop it, it's going to hurt. If I hold a bowling ball 20 feet above your head and drop it on your head, you might die. Right? It's not just going to hurt. You could actually die from that. And so the bowling ball is going to pick up speed. Okay. The paratrooper, whatever this is, doesn't because of the parachute, but a bowling ball doesn't have that parachute. So it's not just going to gradually fall. Okay. It's going to fall and it's going to pick up more speed until it reaches terminal velocity. Something you'll talk about in high school. But for right now, let's see what this looks like. They also drop at 300 feet in the air. Ouch. That would definitely kill you. They hit you in the right spot. Okay, so that's 300 feet up in the air. After 1 second, it's at 284. So we know 285 was right in the middle, so 284 will be right below that. So far, it looks linear to me, but I've only graphed 2 points. You have to graph more than 2 to make sure it's not linear. After 2 seconds, it's at 236. 236 is just below 240, so we'll say about right there. Yeah, that doesn't look linear. 3 and then 156. Okay, so that's 150. So 156 is going to be right around in that area, maybe. Just guessing. And then after 4 seconds, it's 44 feet from the ground. So this is 30. 45 would be right in the middle. So I'm going to put it right in the middle because it's 44. It's close enough. Okay. So that 5 points, 1, 2, 3, 4, 5. Okay, so its graph is going to look like this, which looks like, again, half of a parabola, but this would be a negative parabola because it's been flipped, okay? Because the object is still falling, so it has a negative slope. It's just that it keeps picking up more speed, okay? 4 seconds after it drops, it's a lot closer to the ground than what it even was at 3 seconds after it dropped, okay? So this is nonlinear for this one. Let's compare. You can tell it's linear because it's decreasing 15 every time it increases by 1. Decrease 15, decrease 15, decrease 15. It's always the same. It's constant. Let's look at this one. Decreases by 16. Then it decreases by, I don't know that off the top of my head, 284 minus 236, decreases by 48. And then it decreases by, let's see, 236 minus 156 decreases by 80. So you can see it's just picking up speed. Then it decreases by, I should be able to do that in my head, but I want to make sure I get this right. 156 divided by 44. Yep, 112. Good. So it keeps getting faster and faster. I want you to compare, though. If you look to see, it's actually getting, what is this? Difference of 32, difference of 32, difference of 32. The rate that it's increasing by is actually, it's getting 32 feet per second faster in between each second. So that's why it's not nonlinear, but you can see that the difference is actually going down by 32 each time. So there's a difference of 32, difference of 32, difference of 32. That doesn't necessarily happen for every single parabola in the world, I don't think, but it does for the last 2 that we've looked at. Just a little side note on that. So yeah, definitely nonlinear for this. Graph the data, compare the 2 graphs. Yeah, I think that's all they wanted us to do there. Okay. Now they want us to tell whether these are linear or nonlinear and explain by showing your work. Okay, so I'm going to show work on this one. From 2 to 11, the slope for this, it's increasing 9 over 2. So I've got a slope of 9/2 or 4.5. Okay, then it's increasing by, let's see, what is that, 22? Increases by 2. Okay, so we went from a slope of 4.5 to a slope of, 11. That's a different rate of change. This is nonlinear. I'm just going to put NL for nonlinear. You can do that on your work paper. That's fine. Okay. Now, be careful. Just because these numbers are different doesn't mean it wouldn't be the same. For example, if this increased by 18, which it doesn't, and this increased by 4, 18 over 4 is the same as 9 over 2. So that's still the same. So be careful. Just because these two numbers are different doesn't mean it can't be the same. But if these two numbers, like if this number is different and this number is the same, yeah, there's no way that can be a constant rate of change. This is nonlinear. Example B, I don't need to show any work for this one. You can tell it's nonlinear by the way that it curves, right? This is actually the function, I believe, 0, plug in negative 2. I'm not sure exactly what function this is, but it looks similar to a function that looks like this. The x cubed function has the same shape. My guess is that they've got a number in front of that term, and I'm just trying to figure out what they've scaled it by. But it's got the general shape of a cubic function. Because we know when we cube a positive number, we get a positive answer. When we cube a negative number, we get a negative answer. And if we cube 0, we get 0. So you can see 0 zeros right there. They've obviously scaled it by something. Off the top of my head, I can't see what they've scaled it by. -2 1/3. Yeah, I won't worry about it. It's not a big deal. Okay. Example C, is that a linear function? Of course it is. That's definitely linear. Did I put nonlinear? Yeah, it's definitely linear. And then it has a function, a formula of y equals, it's got a 0 slope, but it crosses the y-axis at -2. So then y equals -2. On your homework, read the note that I attached to your homework. The note that I attached does not say that you don't need a work paper. The note that I attached to the 6.4 says that if you get a function that's linear, I want you to write the slope-intercept form of it. Okay, I know that Big Ideas doesn't have you do that, but I want you to, because on your next test that's coming up, if you don't write it in slope-intercept form and you just say it's linear, you get it wrong. So make sure you know not only that it's linear, but that you need to write it in slope-intercept form. Now, if it's nonlinear, I haven't taught you how to write the equation for that yet. So don't worry about writing the equation, only for the linear ones. Example D, as the rise decreases by 5, the run increases by 7. So this is linear. Because it's linear, I need to write the equation for it. Okay, so the equation for it, we know the slope is -5/7 times x, and then they give you the y-intercept being 25 because x is 0 when y is 25. So that was easy one to do. Y equals -5/7 x plus 25. Example E, this is definitely nonlinear, although I will say it's made up of 2 different straight lines. The function itself as a whole is not linear. It changes course. You've got a positive slope, and then it switches to negative slope. This is actually the base function for absolute value. Okay, for absolute value. The absolute value function actually looks like this. That didn't cross exactly where I wanted it to. That's the absolute value function. Because remember, absolute value can never be negative. If I take the absolute value of a negative number, it's positive. So if I plug in a negative number for x, it still gives me a positive y number. Okay, and if I plug in 0 for x, I get 0. So why is this one giving me negative values? That's because this one has been inverted. So a negative in front of the absolute value symbol. It also has been shifted up to. So next year in your Algebra 1 class, you would say the function here is negative absolute value of x plus 2. Because it's been shifted up, that's what the y-intercept is 2. And so here's what I mean by that. This hopefully should work, unless there's something I'm not seeing here. Let's say I plug in 3 for x. Okay. If I plug in 3 for x, I'm not sure why I put parentheses around that, then it should be negative 3 plus 2 or negative 1 for y. Okay, I'm not getting negative 1 for y. And I'll tell you why I'm not getting negative 1 for y. That's what it would look like. The function that I just drew, or the function I just wrote, actually looks like this, where see it has that slope of 1 each time. This one is a little bit thinner, not wider, but thinner, which means they've scaled it just like the last one we looked at. They've scaled it and they put a negative number other than just negative 1. So maybe it's like negative 2 or negative 3 or something like that. When I plug in 3, I'm supposed to get negative 4. Oops. I'm starting to hate Notability now. Okay. So they've scaled it by something other than just negative 1, but that's the base function of what it would be, just the base function. And then once you have the base function, just like if I said, hey guys, that's what a line looks like, and you're like, is that the all lines look like that? No, not all lines look at that like that. I could make it steeper, I could make it negative slope, I could do a lot with it, and that's kind of what they've done here. So I need to write nonlinear. And then I don't even need to write the function for it, so you don't have to waste your time with that. Example F says, when I decrease by 4, I increase by 2 for the run. Okay. Ooh, but if I decrease by 2, so that number's changing, then I increase by 1. Is that constant? Well, let's see. Is decreasing, is rising negative 4 and running 2 the same as rising negative 2 and running 1? The answer is yes. Both of them give you a slope of negative 2. This slope never changed at all. They just reduced it. And so that is going to be linear. And let me get rid of this extra stuff. Oh, I need that negative 2. The slope then for this, just need one of those, or the slope is negative 2. The equation is going to be y equals negative 2 x, and then the y-intercept, they give you the x-intercept, they don't give you the y-intercept. The y-intercept is when x is 0. So let me go ahead and reverse this and go backwards 2. And then reverse this. So instead of decreasing by 4, I would actually increase by 4, and that's going to put me at 12. So when x is 0, y is 12. This is a method I can use if I can easily get to my x being 0. We looked at a problem on the homework, the 6.3 homework with the bunny hop, where you can't do that. You have to use point slope form, which if I use point slope form, I would get this answer. But this one's a little bit easier, and I can actually just get my y-intercept by thinking a little, backwards about it. Now it wants me to determine whether it's linear or nonlinear, but it's not giving me charts or graphs. It's giving me straight up equations. So for example A, I know this is linear. How do I know it's linear? Because it's written in slope-intercept form. The slope is just 0 for this. The slope is just 0, but it crosses the y-axis at 4.7. Okay, so this is a horizontal line, so I know it's linear. Okay, for example B, this is also linear. How do I know it's linear? Because pi is a number, and so it's just saying y equals 3x, except y equals 3.14x. Okay, so this is just going to be a line that looks like that. Just going to be a little bit steeper, right? Looks like that. So that's linear. Example C. This one is nonlinear. Now, if you're thinking, whoa, 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 I don't see an exponent with that. I thought you said that if the exponent wasn't there, that it was linear. Okay, well, here's the problem. This x is in the bottom of a fraction. Do you ever type an equation in on Big Ideas and you accidentally put the x with your fraction and it marked it wrong? This is why. Because this is actually the same as this. Because it's in the bottom of a fraction, it actually has a negative exponent, not a positive exponent. So this is nonlinear, okay? And you don't need to know that because we're actually going to be talking about negative exponents here in a couple chapters. But you do need to know that if x is on the bottom of a fraction, that's not good, okay? X has to be, x should be off to the side or at least on the top of a fraction. Is this one linear or not? Well, let me see. If we distribute the 4, I get y equals 4x minus 4. Yeah, I'd say this is definitely linear then, because it'd be written in slope-intercept form. Ooh, this x is in the top of a fraction, but that's the same as y equals 4/3 x. The x can just go off to the side, no harm done there. So it just can't be on the bottom of the fraction. If it's on the top of a fraction, it has a positive exponent, a +1. That's good. So this one's definitely linear. Okay. There was a question on your homework that I can't remember exactly what number it was or what it was, but it asked you to graph something like this. And I said that that was the same as doing 1/2 x and using slope of 1/2. I don't even know if it was x over 2 or x over 3 or whatever it was, but that's the similar thing, similar to what we just did right there. And then example F, this is definitely nonlinear because the x has an exponent of 2. So it's going to be a parabola. Last one says account A earns simple interest. That's I equals PRT. Account B earns compound interest. Now, you haven't talked about compound interest and you won't until you get into high school. It has a complicated formula. Simple interest is what, if you take out a loan for a house, by the way, that's called a mortgage. If you take a loan out for a house, it uses simple interest. It just charges you interest on the principal. Compound interest doesn't do that. Compound interest, after the interest has been applied, it continues to change the principal number that you keep finding the interest by. So the rate of change each time changes. Compound interest is what credit card companies do. That's how people get into credit card debt so badly. They borrow maybe $5,000, which they didn't have. After, I'm just using examples here, after 1 month of not paying that back, the $5,000 goes to $5,015. After 2 months, it goes to $5,035. So it increased by 15 each time. It's increasing by a different number each time. Then it goes to $5,060, and then $6,000, and so on and so forth. And it, oh, sorry, 6,000, 5,100, and just keeps going, and it keeps snowballing into something bigger because the rate of increase keeps increasing. And so they've graphed account A, which was just using simple interest. Yes, the amount of interest you pay goes up, but by the same amount each time. For B, the balance is also increasing, but it's nonlinear. So it wants you to compare them. Well, I guess, you know, A would be linear and B would be nonlinear. Let's look at the chart though. At year 0, looks like you put $100. Actually, this is not money that you're borrowing then. This is money that you have in an account. So some of you might even have a savings account that your parents opened for you. So you put $100 in on year 1. Okay. A year later, you come back. Both of these increased by 10, right? You can't even tell a difference. Year 2, you come back, increased by 10, by 10, by 10, and by 10. But on the account B balance, increases by 11, increases by 12.1, increases by, oh my gosh, I can't do the math, 13.31. I think that's right. Don't quote me on that. Then it increases by a different amount. I'm not even going to try. It's nonlinear. You can tell because the rate of change keeps increasing by something different each time. Okay, so that's pretty much it on the homework. As I said, as you're doing these homework questions, if they ask you if it's linear or nonlinear and the answer is linear, make sure you write that equation of that graph so you're ready and prepared for your test. Okay, write it in slope-intercept form. I will see you guys tomorrow, hopefully.